Okay, so let's take a look at graph and network and how you can use graphs in Mathematica. So basically graph is a collection of vertices connected by edges. So the graph consists of, let's say, certain points called vertices, and then some of which are connected by edges. So here we'll take a look at some of the examples that shows you how to get the graph and do various operations on them. So basically this comes under graph theory, which is a study of graphs and its properties. So let's open a new notebook and let me resize this. Right, so let's take wolfram language input, and here we type in graph. Right, so inside graph what we will do is we will have a direction from 1 to, right, so this would be undirected graph, so it will go from 1 to 2, and then let's say 2 to 3, similarly 3 to 1. Right, so when I hit shift enter, it shows you the undirected graph. Right, now there is also directed graph that shows you direction from one edge to another and then back. So let's take a look at that. So let's clear this. So select all, clear. Now here let's type in graph, and within that we'll try to go from 1 to 2, right, then let's say 2 to 3, right, and then 3 to 1. Right, so this is more of a directed version of graph. Notice that we are going from 1 to 2, 2 to 3, 3 to 1. So here the direction is involved. Right, now similarly if you want to have specific data for this graph, what you can do is you will call for certain data sets that can plot your graph data. So type in graph data, and then we will point out to, let's say, some of the graphs like papers graph. Sorry. Right, so for some reason it is not selecting, so let's go with shift enter. Let's find out how it plots the graph data. Okay, it may take time depending on your internet connection. It fetches the data from internet for this specific graph, right, and you get graph data for papers graph. Right, so this is your graph data function. Similarly there is also random graph. So to get that, what we will do is we will use random graph, and it should take your parameters. So let's say if you want 5 vertices in 6 edges, so we can have that. We simply hit and shift enter, and we see our graph showing 5 vertices with 6 edges. You can calculate them. Right, so another thing is checking out our adjacent graph. Right, so select all and then clear. Right, now here for adjacent graph, what we can do is adjacent graph. Right, so it shows that it is adjacency graph. Right, so select that. Right, and then we have to put on some data, so 0 1 then 0, right, and then let's say 0, then 0, then 1, and then we have 1, 0, 0, right? And if I do shift enter, we will basically get the graph generated from this adjacency matrix. So here something's missing, so what that is, we will take a look at that. So we have to add another curly bracket and we get that particular adjacency graph, right? So that covers up some of the typical graph functions like graph data, random graph, adjacency graph, right? Then if you have something like, let's say, graph distance for calculating that particular value, we can have, let's say, if I have grid graph, right? So if I choose this grid graph, and within that we will pass on value, right? 10, 10, 10 and 10, right? So if I use semicolon, we can move to next line, and here I can find out the graph distance, right? And within that then G1 and 10, right? So if I shift enter, it shows me the output for this particular graph distance, right? Similarly, there is also isomorphic graph queue. This function returns true if there are isomorphic graph and expressions, otherwise it returns false. So we'll take a look at that. So we'll try and experiment with the value which should return the negative. So isomorphic graph q, right? So what values it would take is, let's say if I want to take xy expression which is non-isomorphic, if I use shift enter, it returns false. Now let's see another where I want, let's say, value isomorphic graph, and here we have cycle graph, right? That goes to show you it's already a non-isomorphic graph, right? And then another value cycle graph, let's say 4, right? So let me close everything properly, right? And if I use shift enter, it shows false again, right? So that was for isomorphic graph queue function. Similarly, there is also one more function which is specific to getting your highlighted graph. So it highlights the edges, vertices and subgraphs. So what we will do is we will get wolfram language input and that highlight graph, right? And within that we will have complete graph, right? And which should take input 5, right? And let's say another being 1, 2 and 3, right? So if we do shift enter, it should show me highlight graph, right? Notice that it points to 1, 2 and 3 within your graph as well with this red color over here, right? So that was for highlighting vertices 1, 2 and 3. You can change that to, let's say, 4, 5. So if you want, let's say you have 2, then 4, then 5, right? And if you do shift enter, you will find 2, 5, 4 and 5 are highlighted now, right? Similarly, there is also community graph plot. So what it does is basically it takes the data from outside. So let's say if I have National Hockey League data which needs to be represented through this community graph plot. So what I will do is community graph plot, and here let's say if I want example data, and then we will pass network graph and then national hockey league, right? So National Hockey League. Then let's check whether we have properly closed everything, right? So this needs to be within curly bracket, right? Okay, now we can shift enter. Let's find out if it shows National Hockey League data with our community graph. Okay, so as you can see, so within Mathematica you can check for any other similar social data and try to visualize its community graph with this community graph plot. Now there are a few more things that I didn't cover, like let's say finding the shortest path. So usually those are the most important, because when you're working with a graph, then you will try to use something like find shortest path, right? And then within graph, what we will do is we will try to go from 1 to 2, then 2 to 3, right? Then 3 to 4, right? And then 4 to 1. We'll try to go simple now, right? And then 3 to 1 and 2 to 1, right? Now outside this we will also have shortest path points from 4 to 2, right? So if we try and draw the shortest path from 4 to 2 with the available set of our vertices and edges, so here you see 4 to 1 to 2, right? So it tries to get you the shortest path out of that, right? Now there is also one more thing, which is graph with flat list. So let's say if you try to flat the list and try to visualize that data, then you will get the values as well. So for that, what we'll do is we will try to flatten. Let me clear this before. Okay, so flatten. Then next thing is we getting the table of input, which is I to j, right? And then within that I to 3, right? And then j3, right? So once we have this data, make sure we have closed everything, right? Now what we will do is we will also have, okay, let me check, so everything looks right. So if I do shift enter, it should show you the graph of flattened list of connections. So from 1 to 1, 1 to 2, 1 to 3, 2 to 1, 2 to 2, 3, 3 to 1, and so on. So it will try to make the connection and create the graph out of this flattened list of connections, right? So you have some of the functions to play with within Wolfram language for working with this graph and network.